remember them. Okay, so acid-base reactions. So when acids and bases react with each other, protons are exchanged. So we looked at that just a little bit before. So what we need to do is now symbolize this in terms of an equation and see exactly what's happening. So here we've got a generic example of HA, which is the acid, donating a proton to the base, which is B. Positive and negative ions are produced. So you can see here, here's your acid, there's your base, that produces BH plus and A minus. So you can see here that the base has accepted the proton from HA to form BH plus, and then the A is then left behind, which is the A minus. So this is what we class as an acid. So this is from year one chemistry. So that's what I mean, you would have seen this. The reaction's always in equilibrium, okay, so it's a reversible reaction. And so if we add more HA to this, and you would have seen this in the previous, I've done a previous video on this to do with equilibrium. So basically it's how far, that's the name of the video, so how far, so have a look at that. But this is to do with Le Chatelier's principle. So if we add more HA or B, then equilibrium will shift to the right to use it up, so we'll produce more of this. If we increase the amount of BH plus or A minus, equilibrium will shift to the left. So you need to be aware of that in terms of Le Chatelier's principle. So a lot of these topics interlink with each other. Although the videos are done in separately, because it would take me nearly probably a whole week to do the full lot, but they're done separately just to break it up a bit, but they do interlink. And I think that helps quite a lot, because instead of seeing them in isolation, you're seeing it as one, and that helps you to remember it because you're making connections. So water behaves as a base when acid is added to it. So notice in this reaction that the water molecule has accepted a proton to form the hydroxonium ion. So here it is here. So here's the acid, HA, reacting with the water, okay, the water molecule. And water here is actually accepting a proton to form H3O+. So water is actually a base in here, and HA is the acid. Okay, so remember, always look for where that proton's going. So with strong acids, remember, equilibrium lies well over to the right, okay? And with weak acids, equilibrium lies well over to the left, so it doesn't dissociate that much. Okay, so now we've got to the most of the acid stuff out of the way. So the basic principles of what an acid is, what a base is, how that correlates with H plus and OH minus ions, and what a strong and weak acid is. What we can now do is really get into the flesh of this. And we start to look at some of these phenomena, such as Kw, for example, which is the ionic product of water, and you'll also see, for example, Ka a little bit later on as well. So there's a lot of these. So don't get them confused with Kc, which is to do with which is nothing to do with acids and nothing to do with acids and bases in this sense here within this topic. So water exists in equilibrium with its ions. So we've seen that already. So in other words, a glass of water doesn't just contain H2O molecules. Okay. So water dissociates into hydroxide ions and hydroxonium ions, as illustrated in this equation, but also we've seen that before as well. So for example, two molecules of water will break down into the hydroxonium ion, which is H3O+, and your hydroxide ion, which is OH-. Remember, this can be simplified to H+ as well. So this is probably easier to work with, but you've just got to be aware that H+ really exists as H3O+. Okay, so the equilibrium law can be applied. So this is where I said regarding Kc. So this is an element of Kc, but it's specifically to do with water. So the equilibrium law can be applied as we have an equilibrium reaction. So we can use the Kc expression that we'd seen in a previous video to do with equilibria to represent the reaction. So we've got H+, OH-, and H2O. So remember, it's always product over reactant when we're looking at equilibrium laws. So water dissociates into its ion very weakly. It doesn't break up very readily. If you had a glass of water, most of it would still contain the full H2O molecule. You won't have many of these ions. In fact, there's so little OH- and H+ ions compared to the water molecules, the whole water molecules, that we assume that the concentration of water has a constant value because it dwarfs the amount of water molecules in there compared to OH- and H+, completely dwarfs that. So we need another expression to take this into account effectively. So if we multiplied the two constants, Kc and H2O, so the constants of them, then we get a new constant which is called Kw. We call it the ionic product of water. And the units of Kw are moles 2 dm to the minus 6. So you must remember that. So we use a different constant for water. It's always a little bit different. Something so simple has to have its own has to have its own constant effectively. So it's still to do with equilibrium, but it's just a special type. And here it is here. So Kw equals H plus OH minus ion. The H2O bit that was in the Kc expression, you can see there, has been removed because of this assumption that we make. And so this is the formula that we use for Kw. Okay, so let's delve into Kw a little bit more. So important points to do with the value of Kw. So the value of Kw is the same in a solution at a given temperature. So there's no difference there. It's the same with Kc as you've seen before. And Kw always has a value of 1 times 10 to the minus 4 moles 2 dm to the minus 6. Okay, so that's the value of Kw. And this value changes if the temperature changes. So that's the standard value that we use, the benchmark value that we use for Kw, unless the exam board will tell you otherwise if it's in your exam. So pure water has an equal amount of H plus and OH minus ions, because if you're going to, from one water molecule, you're going to have, for every H plus ion, you're obviously going to have an OH minus ion. So we have an equal amount. So when we're referring to pure water, in other words, there's no other elements in there, just 100% pure water, we can simplify Kw to H plus squared, okay? Because we can assume that the amount of H plus ions is the same as the amount of OH minus ions. Okay, so let's look at the pH equation. So pH is a logarithmic scale that measures the concentration of H plus ions in solution. So you would have seen this from GCSE, probably well before GCSE, the pH scale. So it starts from 0 to 14, 0 being very acidic, so a strong acid, 14 being very basic, so this is a strong base, and 7 is neutral, so that's bang in the middle. So the equation we use is pH equals minus log to the base 10 H plus ions. The H plus ions come from the solution, and the logarithmic scale is what you'll find on the calculator. But we'll look at that in a moment. So pH can be calculated when we know the concentration of H plus ions. So if we know the concentration of H plus ions in solution, we can work out pH. So for example, calculate the pH of 0.03 moles per dm cubed of hydrochloric acid. So we know that hydrochloric acid is a strong acid, so therefore we assume that the HCl molecule dissociates fully into H plus and Cl minus ions. So what this means is that the concentration of H plus ions will equal the concentration of the HCl where it's come from. So we can see here, HCl dissociates to form H plus and Cl minus. So using the equation, we can calculate pH. So pH is minus log to the base 10 of 0.03, and again you'll have that on your calculator. The automatically is base 10, and the pH is 1.52, which seems reasonable because it's a strong acid. So the concentration of hydrogen ions can also be calculated when we know the pH, so we can effectively work backwards. So calculate the concentration of hydrogen ions of nitric acid with a pH of 1.7. So we're given the pH, we have to work out the H plus ions. So all we do, and here's the calculator, is we just inverse the pH equation to give H plus equals 10 to the minus pH. So how you get this bit is on the calculator. So if you click shift, press the shift button first, then this bit, there's your normal log button. So you press that and you can see it comes up with 10, and it'll come up with a little square that flashes, and in that square you put in minus the pH that you've been given. So that's 1.7. So what you should get is an answer which is 0.020, and if you put that in your calculator, you should be able to get that same answer as well.